All right, so let's skip priority queues because we can do them if you like, but there it's harder. So, oh, and then remember we did these adaptive queues. We did that for Dijkstra's algorithm, right? Because remember, it's a priority queue. And how do you store priority queues? You store them in a heap. And as you find new edges, you have to change the priorities of their nodes. So you update their priorities, and then things bubble up and down the heap, right? All right, so depth first search. This is, if you like, everybody should know XKCD. It's pretty funny. This one just says that if you do a depth first search, which means, you know, I have this task and it has this first thing, so I do that, and then it has this first thing, so I do that, and you keep going further and further down into the rabbit hole, and you never actually shower, and your date comes, and that's a problem, right? So that's depth first search. All right, so what are we doing here? We're doing the same as before, except with a stack. So we're going to first do it, and we're going to see it doesn't quite work. So we're going to fix it, and then it's going to work just fine. All right? So we start with all right, so initially S has been found and not handled, right? So we see S and we pop S and we put on its children, right? And then maybe B is on the top, so we pop B and we put on its children. And then we pop E and put on its children. And you can see that the picture you get is going to look like this, right? Everybody see that? Right? Why? Because we put on S's children. This was the last one we put on. So then we put on its children. And this is the last one we put on. So we put on its children. And it's not the picture we want, right? Picture we want is this. So the difference is that we're not going to, when we look at S, we're not going to handle all its edges. We're only going to handle one of its edges. So nodes are going to be partially handled, right? So that's what we're going to, and the picture, we're going to, so here's another picture, is at every point in time, what's on the stack is going to be a path from S, right? And so these guys have already been on the stack and come off the stack. They're completely handled, right? These guys here are partially handled, right? What about S? Well, S, we handled this edge and this edge, and we're in the process of handling this edge, right? This guy here, well, we've handled that one, and we're in the process of handling this one, right? And so this is a path of what we're currently working on, right? And you can see that this guy here is at the top of the stack, and so these guys haven't been found. And what are we gonna do next? We're gonna come down and handle its first guy here, right? So we would come down here, and then this is done. So we would pop back up, and then we'd come down here, and this is done. We come pop back up until all of these are handled. And when this is completely handled, we'd pop up here and go down here, right? Does that kind of make sense? Right, so that's our guy. All right, so let's do it. Initially, what do we say? Well, we found S, and we've handled 0 of its edges. So we pop what's off the top of the stack, which is S0, and it tells us we've handled 0 of its edges. So what do? We handle its first edge. So the S0 comes off, S1 goes on, and then we follow the edge, the first edge from S, and we get to A, right? And so here's the path, right, is on the stack. And this says, hey, we've gone down S's first edge. We haven't gone down to any of A's edges, right? So from A, what do? You go down A's first edge, right? And then we go down C's first edge and down H's first edge, right? And now what do? Right? There's no edges leaving H. Okay, we're at K. There's no edge leaving K. So we say K's done. So we pop K off the stack, right? And as we pop it off, we change the color to being, this is going to be part of our depth first search tree, right? The orange stuff will also be part of our depth first search tree, but right now it's on the stack, right? Everybody see that? And now we say, oh, look at H. We've handled H's first edge. So what do? We handle H's second edge. Oops, H has no second edge, right? So H comes off, right? This is just noting that these are the guys on the path and this is a tree edge, right? Just what I said. All right, so then we pop. And now we've done C's first edge. So we come down and we do C's second edge, right? And then we come over to I's first edge, which is to H. All right, everybody buy this? Now, I made that edge purple. Why is it purple? Yeah, you'll see H is already completely handled, right? So it's not going to be part of our tree. We have things called back edges and cross edges, and we can try to keep track of which are which, but I don't really care which are which, all right? So H goes somewhere, we're going to ignore it, right? Cross edge or handled edge, right? It's a cross edge because it's going to a handled node, right? It feels cross in the tree, right? And now we go to K, it's also the same. We go to L, yeah. I'm going to say each node knows whether it's been found and, right? Each has breadcrumbs on it, right? So I would say every node has one of three statuses. It's been completely handled, it's still on the queue, or we haven't found it yet. And when I go over to H, it knows which of those three it is, right? Yeah. Yeah, yeah, yeah. In fact, we saw H when we came down, in which case it was on the queue, and we noted that it was on the queue. And when we flowed back, it came off the stack, not the queue, it was on the stack. So then when we came back, it came off the stack. And when it came off the stack, we noted that it was off the stack. And so now when we go from I to H says, hey, dude, I've been there already. I gave up the office, leave me alone, right? So then we go down to L goes over there, right? And then then we can go up to there and then to there and to, now this one's red. What's special about this one? It's partially handled, right? It's on the queue. It's in the stack already, right? So if it's in the stack, we're going to call it a back edge because it's kind of going up the tree, right? And anybody notice something that's right here? It's a cycle. Why is it a cycle? Well, one of our loop invariants is that what's on the queue is a path, right? And now we have an edge back up. So that gives us a cycle, all right? So these back edges are useful for finding cycles, right? So we say, hey, this is the back edge. It's because it's on the stack. It forms a cycle. That was exciting. All right. And then we keep going, right? From J, we go down to M. And, right, we keep, now we're coming back. We go up, right? We did all this work. Oh, we've seen S before. And then we pop, right? We did all that work. And what did we do? Well, we found everybody reachable from S. Oh, sorry, everybody reachable from S via A, right? If you can get there via the A, we found you already. But maybe, right, we haven't found D yet. So now we say, oh, look we've handled S's first edge. So what do? We go down S's second edge. Right? Does that make sense? And then from there, we search out until we pop back up. Then we go down S's third edge, S's fourth edge. We go down, we pop back up. Now we've handled S's 4 edges. S only has 4 edges, so we're done. Right? We pop the stack. Stock is empty, we're done. Everybody get that? And yeah. No, you mean that last test question? No, you were supposed to do layers. And so you're doing depth first search, so you should have used the Q.
Layers, but from bottom to top. Would EFS do it?
Well,
like from
yeah, I mean yeah. Yeah, I mean it's going to if you I mean you can print them when you find them, or you can print them when you handle them. If you print them when I don't know if I have those slides here, but one thing we cover in 3101 is if you print them in the order in which you pop them from the stack, then what you get is called a total ordering, i.e. if there's an edge, you handle this guy gets printed before this one. And right, and we might cover that here. All right, so here's just the same. It's the same as we were doing before, right? We pop UI, we follow the I plus first edge, and if V hasn't been found, right, then we find it, and we know its parent, and if it's found but not completely handled, then it's a back edge, which creates a cycle, and if it's completely handled, then we have a forward edge or a cross edge, right? Another way of thinking about it is, yeah. We're going to do it. There it is. All right, so here so there's 2 ways that you can write this code. Here we wrote it using a stack, right? But you may know stacks are also used for recursion, right? And so you can also do this recursively. And so here's a recursive depth first search algorithm, right? And the precondition is that you're given a graph in a node S, but also that some of the nodes have breadcrumbs on them, all right? And the postcondition is that from the node you start on, any node you can reach without, you're not allowed to step on breadcrumbs. Any node you can get to without stepping on breadcrumbs, you want to put breadcrumbs on and say hello, all right? That's the algorithm, right? That's the problem. All right, so what's the code? Well, if you need a base case, suppose I'm starting at S, and S already has a breadcrumb on it, it's already marked, one of these X's, then I do nothing, I'm done, I just go home, right? That's the base case. Otherwise, Here, we're given this general graph. I given some S. And what do? Is the first thing I do is I put a breadcrumb on S, right? So there's my breadcrumb on S. And then what do is I loop through all my edges and I recurse on each of them, right? It's just what we were doing before, right? I have a node. What do is I recurse on all my neighbors, right? But here it's not a tree, it's a general graph, right? Before, my neighbors were my children, but now there's no sense of a tree, it's a general graph, but I'm gonna recurse on my neighbors. So what happens is, right, I put breadcrumbs on S, and then I come down to A, right? A is now my new S. And what's my friend gonna do? My friend's gonna put breadcrumbs on every node you can reach without stepping on breadcrumbs, right? Well, my friend can't go to S, so my friend can't get to these guys over here, right? And my friend's gonna go all, right? We don't wanna micromanage our friends, right? We're not gonna say, well, my friend's friend, what do? That makes you crazy, right? All we know is my first friend magically does what they're supposed to do, which is to put breadcrumbs on every node that you can reach without stepping on a breadcrumb, right? Does that make sense? Yeah. Right, so then we come back. Now it's me again. I'm at S, and all of those have been marked. And now what do is I come down to S, and my friend recurses from S. Recurses from B. I come down to B, my friend recurses from B. And what does my friend do? Puts breadcrumbs on everything reachable, right? So all these guys get breadcrumbs. And then we come back, and it's me again, right? So my friend did all of that. And then what do? I come down to my third neighbor, and I say, hey, friend, recurse from here. And what does this friend do? He says, dude, I'm on breadcrumbs. You sent me down to a breadcrumb. That's no fun. And so he returns, right? And now I've done all my neighbors, so we return, right? Does that make sense? Yeah? Right, right. All right, so I'm going to give you two arguments. The one argument is at any node, you'll say, I get down to this node, then I visit, in fact, why don't we come, right? So in this picture here, when I'm here, I'm going to go down there and do whatever happens, and then we're going to come back. We're going to backtrack, and then I'm going to go down this one and do whatever happens, and then I backtrack. So this is kind of called, this is recursive backtracking, right? I go down here and I try everything from this guy, and then I backtrack, and then I have to come down here and try everybody from here, and I go all the way down, and I come back. So from each node, you follow each direction, right? Every node, I mean, it goes back to our proof of the Wall of China. From every node that we find, we're eventually going to completely handle it. And when we handle it, we followed all the edges from it. And if you follow every edge and follow every edge and follow, you're going to get everywhere that's reachable, right? And then my other argument is using this picture, where you don't micromanage your friends, right? So you just say, what is the post condition of my algorithm? The post condition is every node reachable without stepping on breadcrumbs is reached, right? So what does my first friend do? Well, I'm not micromanaging him. I don't know how he does it, but I know he's going to reach all of these nodes, right? You just trust that he does what he's supposed to do. And then my second friend, what does he do? We just trust that he reaches all of these nodes, right? And you can kind of see, if I go down to each of my children, and each of my children does their job, then I've done, and I've put breadcrumbs on my node, then I've done my job. soon as you say next, did you say, I think you say that V is the next, it scares me. And the reason it scares me is it sounds like an iterative word, sounds like you're writing an iterative algorithm, right? And if you want to go back to the stack, then yeah, the next guy on the stack, that's what we're doing. But here we're not doing an iterative algorithm. So there's no, so the next, there is a next in sense of I recurse on each of my children. So I'm going to do this child, and then I do my next child, and my next child, and my next child. And for each of my children, that child recurses and does their job without me bothering them. Right? Does that make sense?